Welcome to this question on dynamics, where we analyze the acceleration and the tension in the rope of an Atwood's machine. Two masses are suspended from a massless rope over a frictionless pulley as shown in the following Atwood's machine on the right. In part A, we'll find the acceleration of the masses once the system is released. In part B, the tension in the rope, two different ways to confirm our answer. We start by adding the forces to our diagram. We have a force of gravity, Fg, acting downwards on the 8 kilogram mass. We'll call this Fg8. We have a slightly smaller force of gravity acting downwards on the 6 kilogram mass. We'll call this Fg6. Tension is an internal force that acts equally throughout all parts of the rope. We represent this by adding a force of tension coming out of the 6 kilogram block and a force of tension coming out of the 8 kilogram block. Once we lay this system flat to analyze the acceleration, you'll notice that the tensions are equal in magnitude and opposite in direction. As all a pulley does is redirect the force, let's lay this system flat now down here so that we can start by solving for the acceleration in part A. All that I've done down here is taken the forces that are being redirected around the pulley and drawing the system as if the pulley wasn't here. Now to start this question, we're going to have to assume which way it accelerates, and I'm going to assume in the direction of the 8 kilogram mass, and I think this is probably pretty obvious to most people. Now the thing is, if you make this assumption incorrectly, once you solve for the acceleration, all that's going to happen is you get a negative acceleration. The number is still correct. The negative indicates that you assumed your acceleration in the wrong direction. So you can just state that you assumed it in the wrong direction and still keep the same number. So there's actually no fear of going in the wrong direction, but I think we all know that this is going to accelerate in the direction of the heavier mass. In our flat diagram, that means our acceleration will be to the left towards Fg8. When analyzing for the acceleration, we're analyzing for the entire system. So let's draw a box around the entire system so that we know what we're analyzing in part A. You'll notice in part B, we'll draw two smaller boxes as we analyze the 8 kilogram and 6 kilogram systems individually to find the tension. We start with our standard equation of force net. Force net is equal to the mass multiplied by the acceleration. We break our force net up into our winning forces, our winners, and we subtract from that our losers. And that's equal to the mass multiplied by the acceleration. In our question, we're going to say that our winning forces are the forces that go in the same direction as our acceleration. So all we have to do is look at our arrows. For instance, Fg8 is a winning force because it goes in the same direction as our acceleration, to the left. Our first tension here is a losing force because it acts in the opposite direction of our acceleration. So let's write this down. Fg8 is a winning force. It goes in the same direction as our acceleration. Force Fg8. Next, moving from left to right, we have tension. Tension goes in the opposite direction as the acceleration, so we subtract the tension. Our next tension goes in the same direction as the acceleration because remember our tensions are equal in magnitude and opposite in direction. So this second tension is a winner. It's a positive force. And finally, Fg6 acts in the opposite direction of our acceleration. So by our definition, that's a loser. So we subtract Fg6. And this is equal to our mass. Our mass, because we're analyzing our total system, is our total mass, mtot, multiplied by the acceleration of our entire system. Looking at our formula sheet, we have Fg is equal to mg, so we can substitute this for Fg8 and Fg6. So Fg8 is equal to m8 multiplied by gravity. Our tensions here are equal in magnitude and opposite in direction, so we can just cancel these out conveniently because we don't have a value for tension at the moment. Next, we have subtract Fg6, so this is again using our equation for Fg m6 multiplied by the value of gravity, and this is equal to our m tote, which is just our 8 kilogram and 6 kilogram masses added together because they accelerate together. So m8 plus m6 multiplied by the acceleration. Substituting our values, m8 is equal to 8.0 kilograms multiplied by gravity, which is 9.81 meters per second squared. Subtract m6, which is 6.0 kilograms, multiplied by gravity again, which is 9.81 meters per second squared. And this is equal to m8, so 8.0 kilograms, plus m6, so plus 6.0 kilograms, all multiplied by the acceleration. 8 times 9.81 gives us 78.48 newtons, and I'll keep extra decimal places all the way through this calculation to avoid rounding errors. 6 multiplied by 9.81 is minus 58.86 newtons, and this is equal to 8 plus 6, which is 14 kilograms, multiplied by the acceleration. 78.48 minus 58.86 is equal to 19.62 newtons, and it's equal to our 14 kilograms multiplied by our acceleration. As our acceleration, what we're looking for is being multiplied by 14. We have to do the opposite to get the acceleration all alone, and the opposite of multiplying is dividing. So we divide both sides by 14 kilograms. On this side, 14 divided by 14 is just 1, leaving us with our value we're looking for, the acceleration. And on this side, 19.62 divided by 14 kilograms is equal to 1.401 meters per second squared. So our final answer for our acceleration is going to be equal to 1.4 meters per second squared. So the answer to part A, the acceleration of the masses once released, would be 1.4 meters per second squared. We'll keep this value with a few extra decimal points for calculating part B of this question. Let's just put it up here quickly. A is equal to 1.401 meters per second squared. And we're now ready to move to part B. In part B, we're asked to find the tension in the rope two ways. We'll do this first by analyzing this orange system for the 8 kilogram mass before moving to this pink system for the 6 kilogram mass. Both systems will give us the same tension if we calculated our acceleration correctly in part A, because remember, our tensions are equal in magnitude and opposite in direction. So let's start by solving for the tension in our orange system, our 8 kilogram system. Finding our tension via our orange system here, our 8 kilogram system, let's just note this here. We start from our standard force equation. Force net is equal to ma, just as before. And again, we're going to do the winning forces, the force of the winners. Subtract the force of the losers is equal to our mass times acceleration. And again, we're going to say that our winning forces go in the direction of our acceleration. Now, our whole system accelerates at 1.401 meters per second, so that also means our two individual systems, our 8 kilogram system and our 6 kilogram system, also individually accelerate at 1.401 meters per second squared. So in our orange box, our 8 kilogram system, we only have one winning force that goes in the same direction as our acceleration, and that's Fg8. So our winning force is Fg8, and we subtract from this our losing force, which is our tension, that points in the opposite direction of the acceleration. And this is equal to the mass of the 8 kilogram block multiplied by the acceleration. It's only the mass of the 8 kilogram block because remember, we're only analyzing the system for the 8 kilogram block. Once again, looking at our formula sheet, our Fg is equal to mg. So our Fg8 is equal to the mass of the 8 kilogram block multiplied by gravity. Subtract from this the tension, what we're looking for, and this is equal to m8 multiplied by the acceleration. Substituting our values, M8 is equal to 8.0 kilograms multiplied by gravity, which is 9.81 meters per second squared. Subtract from that the tension, and this is equal to M8, which is 8.0 kilograms multiplied by our acceleration from part A, which is 1.401 meters per second squared. 8 multiplied by 9.81 is 78.48 newtons. Subtract our tension, and this is equal to 8 times 1.401, which is 11.2 newtons. To get our value for T all alone, we subtract 78.48 newtons from both sides of the equation. So on this side, 78.48 subtract 78.48 is just 0, leaving us with negative T. And on this side, 11.2 minus 78.48 gives us negative 67 newtons. To get a positive value for tension, we multiply both sides by negative 1. So negative 1 times negative tension equals tension, and this is equal to negative 67 times negative 1, which is 67 newtons. So the answer to part B, the first part of part B, is 67 newtons. So the tension from the 8 kilogram system is 67 newtons. Let's note this up here. Tension is equal to 67 newtons. And let's now solve for the tension in the 6 kilogram system, the pink system over here, to confirm our answer for tension, which will also confirm that we most likely got the proper acceleration in part A. To solve for the tension in our 6 kilogram system, our pink system, we again start with our standard equation for force. Force net equals MA. So we're now doing the 6 kilogram system. And we start with force net is equal to the mass multiplied by the acceleration. And again, we're going to do the force of the winners, subtract the force of the losers, is equal to the mass times the acceleration. Again, where our winners will be our forces that are in the same direction as the acceleration. In the same direction as our acceleration in the 6 kilogram system, we have the tension. So our winner is the force of tension, and we subtract from this our loser, our FG6, which is in the opposite direction of the acceleration, FG6. And this is equal to our mass of our 6 kilogram block, because we're now analyzing the 6 kilogram system, multiplied by the acceleration of the system that we found in part A. Fg6 is equal to our mass times our value of gravity. So rewriting this, we get tension minus our mass of our 6 kilogram block multiplied by our value of gravity is equal to our mass of our 6 kilogram block multiplied by the acceleration of our system. Substituting our values, we get tension minus the mass of our 6 kilogram block, 6.0 kilograms, multiplied by the value of gravity, 9.81 meters per second squared, is equal to the mass of our 6 kilogram block, multiplied by the acceleration of our system, 1.401 meters per second squared, as found in part A. This gives us T minus 6 times 9.81, which is 58.86 newtons, is equal to 6 times 1.401, which is 8.406 newtons. To get our value for the tension all alone, we add 58.86 newtons to both sides of the equation. So on this side, negative 58.86 plus 58.86 just leaves us with our value of tension, what we're looking for. And this is equal to 8.406 plus 58.86, which is 67 newtons, confirming our answer from our 8 kilogram system. So we've now solved part B, find the tension in the rope 2 different ways. And because the tensions worked out the same, not only does this give us a large confidence in our math for finding the tensions, it also gives us a lot of confidence that our acceleration from part A was also correct. Thank you for watching this video on dynamics, where we solve for the acceleration and the tension of an Atwood's machine.